Thank you very much for the introduction. Hi, I'm Athiya, and today I'll be presenting to you the technique that I developed to quantify agglomerate-to-wall collisions within dry powder inhalers. So to start off, the focus of this area was to consider powder dispersion within inhaler devices, as this is particularly critical for achieving fine particle fraction and successful lung deposition. So the aim was then to develop a technique that's able to quantify particle-to-wall impaction within these sort of devices. And we did this by starting off with high-speed microscopic images taken from an inhaler device, as the one shown, with two inlets into a swirl chamber and a single outlet through the middle. And then we focused on high-speed microscopic imaging of one particular section that's indicated here, where a significant number of wall impactions occurred. So current research into dispersion in DPIs focuses on three modes of deagglomeration. These are turbulence, particle-to-surface impaction, and particle-to-particle impaction. However, there's very little known about what drives these mechanisms, and while there's been some computational work done, to the best of my knowledge, there is an absence of experimental data that quantifies this phenomenon. So the main challenge in this regard is when you're processing images such as these, when a particle does impact the wall, current binarization and processing methods are unable to distinguish a particle from the surface impacted once contact has been made. So therefore, in order to quantify these impactions and their frequency, a prediction method needs to be used. Which brings me then to the technique that I've been using. So starting with the raw image there on the bottom left, we start by binarizing it, converting it into ones and zeros, and then applying geometric constraints. These constraints will remove any small objects that would likely be noise or anything that's large that would likely be a result of wall deposition. And the remaining objects are then considered to be agglomerates. From here, we can then obtain particle properties such as size that can then be used to calculate the particle's velocities. Based on this information, we can predict the particle's trajectory and estimate its new position in the following time step. Given its geometric data, we can estimate a region within the field of view that the particle is expected to occupy, as shown in green. Where this region where the particle occupies coincides with the wall, we can expect a collision to occur. In order to demonstrate this, you can see in the video here that tracked particles are marked in green. Tracked in this case means a velocity was able to be calculated. And particles that are predicted to collide are then marked in red. You can see from this video then that the main limitation in capturing all of the particles that collide with the wall is that many particles are unable to be tracked in the first place. And this is due to a relatively new code that's being used to calculate particle velocities that is continually developing. So there's potential for this application to improve. So applying this then to mannitol of two powder size distributions at 30 and 60 liters per minute, you can find that at the lower flow rate that the difference in powder sizes has a much more significant effect, which is, as you can see by the figures on the right, is consistent over the full evacuation time. Whereas at higher flow rates, the change in powder size has an insignificant effect on the overall proportion of wall collisions that were detected. So this then demonstrates an ability to measure significant differences in the proportion of collisions when changing flow rate and particle size. Future work in this area would aim to further delve into collision analysis, including agglomerate-to-agglomerate collision and further quantification of dispersion mechanisms. Also developing statistical models that are able to predict the probability of surface impaction. For example, a logit model that determines the probability of prediction for a particular particle based on its properties. Thank you very much.
Thank you. Lovely work. And you've identified obviously a much needed area. Do you have any plans to try and match what you're seeing experimentally with sort of computer predictions of flow dynamics?
Yes, so that would be a following step. To start off with, we've also been training this particular code with simulated data as a training set. And then ideally we'd continue to compare that with simulated data and use it also to train simulations as well.
Yeah, and then going forward, as you develop the technique, how do you see this being applied in the future to optimize inhalers? Where do you see its first application coming?
Well, I think it'll start off by figuring out what mechanisms are driving dispersion in a particular device. And then you can see which, by imaging other areas within the device and also global imaging, you can understand the effect it has on the flow and dispersion as a whole. And that can then be used in terms of optimization for a particular device and determining which mechanism would be most suitable.
Thank you, Athiya. And then I just got a couple of questions. From what I can see, there's quite a lot of manual intervention involved in trying to interpret the visual images and make those predictions of the particles that you think are likely to undergo collisions with the wall. And I guess how do you ensure you can evaluate a representative number of particles to try and get a meaningful prediction of what you think is going to be happening in a practical situation? Because one of the biggest challenges that I've always had in inhaled development is you get hundreds of thousands of particles, and the drug substance ones are the ones that are really small. So actually you have millions of those particles. Mm-hmm. How do you try and get representative data using this technique?
So the current method focuses on largely just the bigger agglomerates, because those are the ones that with impaction will have the biggest effect in terms of dispersion. So in terms of the image processing methods tend to disregard those smaller particles anyway, since they are less consequential for this particular sign. But moving forward, I haven't considered applying that to smaller particles at this stage.
Yeah, just following up on we've got a few questions on related to the particle size question, which is what kind of size ranges can you measure using your technique, and are you getting any insights into how the particle size impacts on other dispersion methods?
Yes, so at the moment, the current imaging method I've been using has a scale of about 5 microns per pixel. So the smallest particles we'd look at realistically would be around 20 microns in diameter. But for the impaction, I've been focusing on agglomerates that are bigger than 50 microns. I'm sorry, what was the second part of that question?
how the particle size of the agglomerates impacts on the different dispersion mechanisms that may be occurring.
Yeah. So in this particular device, we're able to observe that the larger particles were more likely to collide just based on, I'm guessing, momentum and its velocity moving in. Literature also tends to show that for these larger agglomerates, impaction tends to be the most efficient in terms of breaking them up. And that's, we're seeing a lot of that in this as well. But what will be interesting is when we get a chance to compare it to the other modes of the agglomeration as well, and being able to quantify that comparatively.
Thank you.
Okay, thank you very much, and thanks for joining us late in your day and answering all the questions. So.